To start recording.
Yeah, should be.
And can you just check if people online can hear stuff? Just in case.
Yeah, I think Leslie's saying.
Okay, good. Okay, so let's get started. So our colloquial speaker today is Yuan Li from the University of Massachusetts campus. She did her undergraduate work in Nanjing in China, working in Purple Mountain Observatory for her master's, one of the oldest observatories anywhere in the world that's still responsible for the Chinese lunar calendar. She then moved to Columbia University, working with Greg Bryan, after which she was at the University of Michigan for a postdoc briefly at Flatiron, and then the TAC fellow at UC Berkeley, before starting a faculty position initially at the University of North Texas, and then moved to AMPA. So really all over the place. And that in some sense is also reflected in her research, which is also looking at many of the large scales and is all over the place: galaxy clusters, supermassive black holes, galaxies themselves, feedback, turbulence, a lot of it, including work on observations, work on theory, modeling. So I am going to be excited for this because this is going to be a lot of stuff from a lot of collaborators, and it's going to be an adventure whichever way you go with it. So take it away.
Thank you for the introduction. Thank you so much for having me here, and thank you all for coming. So yes, today I will be talking about turbulence in the intra-cluster medium. And yeah, normally I do computational work, but today I'm mostly talking about observational work. Because I'm only a fake observer, I needed a lot of help, and a lot of these amazing people give me the necessary help. Okay, so I'll first start with a brief overview of what we know about turbulence in the intra-cluster medium, or ICM, both from the theoretical perspective and from the observational perspective. And then I will be talking about a relatively new method that I've developed over the past few years to measure turbulence in the intra-cluster medium. And I'll talk about how we apply that to cluster centers, and it helped us figure out how supermassive black hole feedback operates. And we've also applied it to cluster outskirts. And this new method allows us to probe scales below the Coulomb mean free path there, and allows us to put unprecedented constraints on the plasma properties on those scales. So we've all experienced turbulence, right? You've experienced it on the airplane. But when your airplane is experiencing turbulence and you look outside of the window, you may not necessarily see anything obviously turbulent. And that's because we don't see air molecules. But turbulence in this atmosphere is really everywhere. And you see it clearly when there are tracers there. So a lot of the work I'm going to be talking about is about finding smart tracers to help us trace turbulence in places where the medium is harder to observe directly. And here's another example of putting tracers in a turbulent flow. When you pour milk into your coffee, you see turbulence there. And we don't have a full mathematical description of turbulence, but we can describe turbulence with words pretty well. So if I ask you, how would you describe the motions of milk in your coffee? You would probably say that you see eddies or whirls or swirls or twirls of different sizes. And you may also notice that the bigger whirls are breaking up into little whirls, as is beautifully depicted in this Leonardo da Vinci picture, and also at this really lovely poem that says big whirls have little whirls which speed on their velocity, and little whirls have lesser whirls, and so on to viscosity. Oops. Fundamentally, we think that turbulence stems from the nonlinearity of the Navier-Stokes equations that describe the motions of fluid. More specifically, it's the nonlinearity of the momentum equations there, which is really just Newton's second law F equals ma applied to fluids. And it's turbulence is notoriously difficult to understand. A lot of physicists have joked about it, but in a way, I think it's perhaps a good thing for us to study turbulence, because if I don't understand anything, I'm with those brilliant people who also don't understand turbulence, right? So we have through many experiments figured out what kind of conditions would allow turbulence to develop. And it's really just simply sort of decided by the so-called Reynolds number, and that is the characteristic length scale multiplied by the characteristic velocity of the system divided by the viscosity. And another way to think about what this Reynolds number means is the inertia force divided by the viscous force. And as this little experiment shows you, when the Reynolds number is small-ish, so typically smaller than 100, the flow is laminar, meaning it's regular, it's coherent, it's easy to predict. When Reynolds number is larger than 100, then the flow tends to become more chaotic and random and hard to predict. So that's how turbulence develops. We also have a pretty good understanding of the statistics of a steady state turbulent flow. So most of you probably have heard of the Kolmogorov power spectrum, right? So it describes the kinetic energy power spectrum of a steady state incompressible turbulent flow. And on some large scale or small k, energy is injected into the system, and big worlds turn into little worlds, all the way down to some small scale where kinetic energy dissipates into heat. And between the injection scale and the dissipation scale, the kinetic energy is related to k, the power law of -5/3. And you can easily derive this with just simple dimensional analysis, assuming that the rate of energy injection is the same as the rate of energy dissipation, and it's also the same as the rate that energy is cascading down all scales. So that quickly gives you a relation between velocity and size that says velocity scales as L to the 1/3, meaning bigger worlds, bigger eddies move faster. Smaller worlds move more slowly in a turbulent, right? And then once you have the velocity size relation, you can easily derive the kinetic power spectrum, right? So for the most part, I will only be using the size velocity relation. Sometimes I call it a poor man's power spectrum. But these two are very much related. So in most astrophysical environments, we think the effect Reynolds number is very large, and people typically quote 1 million to 1 billion maybe, because the scales are large, velocities are large, and effective viscosity is supposed to be low. Now I will come back to viscosity later. So we expect very large Reynolds numbers, therefore turbulence should easily develop in most astrophysical environments. Now we do see turbulence on the surface of planets, on the surface of stars, our own star, and therefore the wind from our star, or the solar wind itself, is also turbulent. We see turbulence in simulated accretion disks, in simulated circumgalactic medium. We think we see turbulence in the interstellar medium, right? And also in the intra-cluster medium, which is what I will be mostly talking about today. But I should say that the method that I'm using is sort of inspired by the ASM studies, and it has been used in CGM studies. So just to give you an idea of what galaxy clusters are, for those of you who don't think about clusters all the time, this is a movie of a cluster formation and evolution put together by the illustrious TNG team. So you will see how a cluster is assembled in a cosmological simulation. The galaxy clusters are the largest gravitationally bound objects in the universe. They're mostly held together by the dark matter. And as you can see in this movie, throughout the formation and evolution of a galaxy cluster, there are many, many merger events. It almost never stops merging with substructures, right? The way I think about galaxy clusters is that they're basically cosmic trash cans. Lots of things going and things going all the time. And towards the end of the movie, the colors are switched to show where the stars are. But inside a galaxy cluster, most of the baryons are actually not in stars or individual galaxies. Most of the baryons exist in between galaxies inside a galaxy cluster, and they exist in the form of diffuse hot plasma called the intra-cluster medium. And this plasma glows in the X-ray because it's so hot. We see the Bremsstrahlung radiation from this plasma that's shown in blue. And as you've seen from that movie, clusters are experiencing mergers almost constantly. So as you can imagine, these merger events must drive turbulence inside the intra-cluster medium. And cosmological simulations have shown that typically you would expect a few to maybe 20% of turbulent pressure support inside a galaxy cluster. And the intra-cluster medium is an interesting lab for turbulence because the mean-free path, the electron coulomb mean-free path, can be very large due to the low density of the ICM. In cluster centers, the mean-free path is on the order of 10 parsec. In cluster outskirts, the mean-free path is on the order of 10 kiloparsec, which is the size of a galaxy. So observationally, I will show that we're probing below mean-free path now. And as some recent simulations have shown, even if you just include very simplistic speedster viscosity, you would produce very different structures in the ICM.
The mean-free path for which direction?
Well, it's a great question. So for this particular simulation, they're just using isotropic viscosity without thinking about magnetic fields at all. But you're right. That's the next slide. Thank you. So of course, turbulence in the ICM is more complicated than that, right? Because of the existence of magnetic fields. So this is sort of the theoretical picture. And I don't want to explain everything here, but mostly we think the ICM is a weakly collisional plasma, meaning the Coulomb mean-free path is sort of comparable to the scales we're looking at, right? And it's also weakly magnetized with a high plasma beta, meaning magnetic fields are not dynamically important, but magnetic fields are certainly there. It's subsonic, but super alphanic, again, because the magnetic fields are weak. And we think there should be different modes of MHD turbulence, and they may cascade differently, they may dissipate differently. So there can be a lot of really, really interesting physics there that isn't well understood. And this is not the kind of plasma we can recreate in a lab on this planet. And so in a way, I think ICM is a really fascinating plasma lab that the universe has set up for us to think about plasma physics. And I've said previously, a lot of the observations that we can get from X-rays are just probing the very large scales. But with the method that I have developed, we're now probing more interesting scales, maybe possibly potentially looking at partial dissipation of different MHD modes, and also probing the collisionless region. Okay, so why do astrophysicists care about turbulence in the ICM, right? So I talked about why it's interesting from a physics perspective. I think it's also very important from astrophysical perspective because turbulence amplifies magnetic fields. We know that the strength of magnetic fields, even though it's weak inside galaxy clusters, it can't just be from simple compression of the cosmic magnetic fields. So there has to be some sort of dynamo processes that grows the magnetic fields. That's probably related to turbulence. And turbulence is also potentially very important in accelerating high energy particles, cosmic rays. So these really interesting funky structures are actually tracing the relativistic particles. So this is radio-synchrotron emission that I will not be talking about today. I just think this is like a really beautiful image, so I use it everywhere. You know, that's a whole another kind of worm. We don't fully understand, but turbulence is definitely important in accelerating these very high energy relativistic particles. And also on smaller scales, we all know that turbulence regulates star formation and therefore regulates galaxy evolution, right? And if we look at cluster centers, maybe turbulence can also be generated by supermassive black hole feedback. And perhaps it, you know, has something to do with how black hole feedback operates. So I'm pretending that this is a zoom-in view of this cluster. It's not. I'm just stitching them together. But when you zoom into the central regions of many nearby relaxed clusters, you see something like that. So this is the X-ray image, Chandra X-ray image of a nearby galaxy cluster called the Perseus cluster. And you see all of these cavities or bubbles in the X-ray that are caused by supermassive black hole. And I like to claim that cluster centers are the best places to study supermassive black hole feedback because all the footprints are preserved. They're all there. But of course, the footprints are very messy. So we see these bubbles in the X-ray that are presumably inflated by the relativistic jets from the black holes. And so the jets are basically doing work to the surrounding gas, right? So that's one way of doing feedback. At the edge of these bubbles, people have also claimed the detection of shock waves and or sound waves. And the dissipation of these waves will also generate heat, right? So that's another way of black holes doing feedback potentially. And all this messiness also looks potentially like turbulence. And if the jets can stir up the gas, then the dissipation of turbulence can also give you heat, right? So there can be many ways for black holes to do the so-called feedback. But exactly what's happening is kind of hard to figure out from the observations, right? It's always easier to look at simulations. And so that's what a bunch of people did, including myself, a few years ago. So people who did black hole feedback simulations, many of us looked at our own simulations and asked the question, how does feedback operate? How does the energy from the jets get coupled to the surroundings?
So I know that in some cases, they've seen that the radio jets have recessed or moved around over time. Is that an important process in generating turbulence, or is that not really essential for the stirring that you're seeing? Just the precession or the floppiness of these jets.
Okay, that's a lot of questions. So let me first say that I don't think in cluster centers we see a lot of direct evidence of precessing, but we definitely see different generations of bubbles not aligned, right? So that's an older bubble, that's going that way. And these are medium-aged bubbles, they're going this way. And right now, the Perseus black hole jet is actually pointed at us. So
Okay,
something a lot of people didn't know, and I apparently didn't know that, like throughout my whole PhD process, I was just like, well, Perseus black hole is not doing anything right now. But later I learned, oh, it's actually considered a blazar, it's pointed at us. So obviously not pointed that way anymore, right? So it's definitely turning around, what we call it precessing jet, like I don't know, because
Yeah,
this is like a way longer time scale, but that's an interesting question, and I certainly have precession in my model for my jets. Some people don't have it. It makes some difference, but as I will talk about, in terms of turbulence generation, the difference is small, and overall. Obviously, we were all running different models and the exact conclusions were not identical. But we all sort of agreed that the amount of turbulence was small with all different models.
These pictures and the identity of shocks around these intra-cluster
Oh,
regions,
yeah.
they remind me of the model for the acceleration of cosmic rays in clusters, and it reminds me of a lot of sort of work, especially by like Mohawk and stuff like that, to look at cosmic ray feedback. And I was wondering if there was any sort of story to tell here that where cosmic rays feedback to spatial energy through cosmic rays might have an effect on.
Sure, you can add cosmic rays there. So there could be some, well, so we know that the younger bubbles are typically filled with radio emitting plasma. So there's definitely cosmic rays there. We also have constraints on the overall amount of cosmic rays in galaxy clusters from like, I think gamma ray upper limits and stuff. So we know that they're like, there's not a whole lot of cosmic rays. It's different from the ISM where you have more or less equipotation. There, we don't think it's equipotation, so there's less in terms of the fraction of cosmic rays. But can there be still a decent amount of cosmic rays that are helping with the feedback? Yes, I think there's still.
Can you say a little more about the shocks and sound waves specifically, like how much energy is transported in this sort of picture? Like,
So you should read my paper. So now that's actually the sort of one of the main conclusions in my analysis, but you know, it's probably a model dependent thing. In my model, most of the kinetic energy is dissipated through shock waves rather than turbulence. I don't want to speak about reality because that's not the aspect I have analyzed. I think it's probably harder to say definitively. I think for some of these features, the observers agree that, okay, there is a shock wave, but it's usually a weak one. For some of these, I think the observers are, they're still arguing if it's a shock wave or a contact discontinuity. It's kind of hard. And that's one of the things I will mention is the limitation of X-ray observations. I think your photon limit. So from the theoretical perspective, those of us who have analyzed our simulations more or less agree that black hole feedback does not generate a lot of turbulence. But on the observational side, the observers have come up with smart ways of inferring the amount of turbulence in the ICM. So if you look at these Chandra images, you see surface brightness fluctuations, right? It's obviously it's not evenly distributed. And if you can translate surface brightness fluctuations to density fluctuations, which is easy, and then translate density fluctuations to velocity fluctuations, assuming delta rho over rho is proportional to delta p over p. Delta v over v. then you can infer a level of turbulence from the surface brightness fluctuations. And the inferred level of turbulence would give you quite a decent amount of dissipation. Such that in nearby clusters that they've looked at, Perseus and Virgo, the amount of inferred level of dissipation can perfectly balance radiative cooling. And that would imply that turbulent dissipation is a very important heating mechanism. And you may not trust this analysis with so many assumptions, but this was quickly confirmed by a more direct measurement of the ICM velocity. So there was a X-ray telescope called Hitomi that made one observation before it tragically died a few years ago. And that one observation was looking at the central region of Perseus. And what Hitomi told us is that within this big square along the line of sight, there is a non-thermal line broadening that would translate to a velocity dispersion of 100-something kilometers per second. And that is perfectly consistent with what people inferred from the Chandra X-ray surface brightness fluctuation analysis. And so if you think all of that is turbulence, then the amount of turbulent dissipation would be quite significant. And so it seems that the observations and the X-ray observations are indicating that there's a lot of turbulence in cluster centers. And the theoretical models are saying the opposite, right? I don't know if you've noticed, but usually when models don't agree with the observations, people say the models must be wrong. And I disagree. There can be nothing wrong with my models. There must be something wrong with the observations. So what could go wrong with the observation? Well, if I know anything about observations, I know that X-ray telescopes don't have good spatial and/or spectral resolution. And if you want good spatial spectral resolutions, you want to use optical telescopes or even ALMA. And luckily for us, the centers of galaxy clusters are often multi-phase. So in addition to this really, really hot plasma of, a few times 10 to the 7th Kelvin that shines in the X-ray, there's oftentimes a much cooler component that shines in the H alpha. So this is just the example of Perseus. It also exists in this really weird filamentary form. And some of these, we call them filaments or cool clouds, whatever. The H alpha is probing gas with temperatures around 10 to the 4th Kelvin, right? So that's way cooler than the surrounding hot plasma. And a lot of these filaments also have a molecular component that's even forming stars. And so anybody looking at this for the first time would immediately ask, how do these filaments get there in the first place, right? This is like seeing a bunch of ice cubes floating in a bowl of hot soup, right? So this was really, really intriguing to a bunch of theorists. So there was a lot of theoretical effort over the past, at this point, over a decade, trying to understand how these filaments get there and what they're doing. I don't think we've made a lot of progress, but there's still not anything conclusive, super conclusive. I think the mainstream idea is that these cool clouds formed out of the hot intra-cluster medium due to thermal instability. And as I showed in my thesis work, in a somewhat realistic, trying to be realistic, Perseus-like cluster by putting black hole jets, I do see thermal instability being triggered by the jets. So you actually see cool clouds forming preferentially along the jet propagation direction. And this has been shown in many other paper since. So here are some examples, and I want to also highlight my student's recent work. He's writing the papers, and he's also going to be on the job market. If you're on a fellowship committee, you're out. He's absolutely amazing, the best student I've ever worked with. So the point is, these cool clouds are born out of the hot gas, right? So I thought, well, maybe we could look at how these cool clouds are moving to understand how the hot gas is moving. Just like we can look at the motions of leaves to understand the motion of the wind, which is harder to observe directly. And these days, with ground-based optical telescopes that have an eye view, you can not only get the flux of these clouds, but also their line of sight velocities. So here is a velocity map of the Perseus filaments. People looking at these maps will say, ooh, it looks like there's a lack of large-scale outer motion, right? The velocity field looks kind of random, right? Perhaps it's turbulence. But there are ways we can figure out if it is, right? So what I did a few years ago is I just computed the first order velocity structure function of the filaments. And so that's just looking at all the pairs of pixels on this map. And I record the separation of every pair and their velocity difference. And the structure function is just showing the relation between the mean velocity difference and the separation of the pairs. So it's essentially the size velocity relation that I mentioned earlier. And it directly translates to a power spectrum. And as you can see, on small scales, there's a beautiful parallel that looks like a cascade of a turbulence, right? And we can also divide these filaments into inner filaments and outer filaments. And the inner filaments follow the structure function shown in red, and outer filaments follow structure function shown in green. And you can see, okay, there's also a energy injection scale for the inner filaments of about 10 kiloparsec. And that is exactly the size of the bubbles here. It's inflated by the black hole jets. And the outer filaments don't seem to care about inner bubbles, but they seem to reveal a driving scale of about 20 kiloparsec, and that's the size of this outer bubble. Okay, you have a question.
Sorry to interrupt, I just want to make sure I understand this. So we are measuring the pixel by pixel
That's right.
pair line of sight velocity difference. What about the broadening of the line?
I did not use that. So maybe you're thinking about Larson's relation, which uses sigma, right?
Each pixel you have a
That's right.
broadening.
There is a line broadening. I've been thinking about what I can do with it. I think there's information there.
Yes.
I haven't figured out how to use it.
My naive thinking was that give you some information on the pixel scale of the velocity field.
Yeah, I think I have, well, maybe because of my ignorance, because I've never actually touched the raw data. I don't really know how to fit them. But I fear sometimes maybe you have maybe multiple components along individual line sites, and I think it does happen sometimes, and I'm not sure how I would disentangle that, because that would definitely boost your sigma artificially, right? But yeah, we can maybe talk more and see if you have ideas. I've been thinking about how we can maybe somehow build that information in, because there's information. You're absolutely right. I just don't really know how to purify it yet. Yeah, but this is more straightforward because you're identifying the line shift. And my understanding is, well, there's a line, you know where the peak is, right? Maybe it doesn't look like perfect Gaussian. But the observer friends told me, oh yeah, no, the peak is pretty red. Yeah, so that's what I was using. And you get pretty good statistics with just the peaks down. So yeah, we thought we were not just detecting turbulence, but we were detecting turbulence directly driven by the black hole activities. And then we looked at two more clusters. We saw the exact same stories in this, in particular in MEV7, the driving scale that we infer from the structure function is like not just the size of the bubble, but also you can see the size of this cute little jet that's still actively inflating the bubble. So we said we detected black hole driven turbulence possibly for the first time. We also checked the agreement with the X-ray measurements. I said earlier, the X-ray data doesn't have good spatial resolution. So this purple line is a surface brightness fluctuation analysis done for a tailored region that sort of matches where the outer filaments are. And you see a perfect, pretty amazing agreement between purple and green, right? Meaning the kinematic coupling between the really hot plasma and this ionized, much cooler ionized component is good on those scales. And these horizontal lines represent the Hitomi results because Hitomi has practically no spatial information because it doesn't have good spatial resolution whatsoever. So the results are just represented by these horizontal lines, but you see good agreement, right? So red corresponds to where sort of the inner filaments are, and green is where the outer filaments are. So at the driving scales, the kinematics of the cool filaments seem to agree really well with the kinematics or inferred kinematics of the hot plasma. We don't know if the kinematic coupling remains good on small scales, and it's gonna be maybe decades before we can probe smaller scale stuff with the next generation X-ray telescopes. So we'll see how good that coupling is, but for now, I'm just gonna extrapolate and say the agreement is gonna be good.
I have a simple, naive, and maybe silly question. Are the stars moving that are forming in these cold gas streams, are they moving towards or away from the central galaxy?
The stars?
You said, yes, they're star forming, you saw.
So there's star form. Well, I'm ignoring star forming here.
But are they moving towards or away from?
They're all over the place, right? So if you look at the velocities of these clouds, they're, some are moving towards us, some are moving away from us.
Good, it's the observer, but what about with respect to the sun?
Oh, wow. We don't have the perspective of the black hole, but you would infer just from looking at this, it's not a coherent inflow or outflow, right?
Okay.
So it looks kind of random. So presumably there's stuff going down, there's stuff going up. And in simulations, definitely there's stuff going down, there's stuff.
Can I ask one more naive question? So the separation here is the projector separation.
Oh, yeah. Oh, you asked a good question.
So if you do the projection.
We don't.
You can.
We don't.
How do you kind of pose this in the comparison with the Kolmogorov spectrum?
Great question. I'm about to get there. The short answer is we don't know the 3D structure of these filaments. So what Yuan is asking is, well, we're looking at projected information, and without knowing the 3D structures, how do you correct for that projection? We can't. We do know the trend. So for this sort of analysis, the projected structure function should be flatter compared with the true 3D structure function, because you would have more, you would have pairs of pixels that are well separated in the real physical space, but in projection they look close, and so they would give you boosted power on these smaller scales, sort of artificially. So we know how it would affect the result, but to what extent is, that's kind of hard because we don't know. It's,
The real 3D is even steeper.
yes, I know where you're going. Yeah, great.
And I comment on that, because it's sparse, right, it's not part of fully filling the 3D space, the small scale should be less, there should be less confounding in the small scale than the large scale, so. Can we not sort of think about the small scale as representing the true distribution of the large scale, and I see the way that it's traveling to have more of the 3D effects.
yeah, so exactly, so you would have some flattening, the smaller scales. Okay, so assuming good coupling, meaning if we assume that whatever we measure for the cool component is what the hot gas would show you if you were able to observe it directly, then we can talk about some interesting plasma properties. Because we're actually probing scales very close to that naive dissipation scale. If you're just thinking about isotropic viscosity, speedster viscosity, so this dashed line is what you would expect if turbulence dissipates at the scales, you naively expect dissipation to happen. And what we measure is that it seems that turbulence continues past the naive dissipation scale. And the previous best constraints come from surface brightness fluctuation analysis that used like 12 days of Chandra time, and I like to brag about how cheap my data is. I got for free from my friends, but it's a lot cheaper and it's probing much smaller scales. And as I will show later, in cluster outskirts, we're really going down all the way to collision regime now. So this is really putting interesting constraints, so-called constraints on the suppression, basically, of effective viscosity in the IC. I mean, in other words, we're thinking about plasma at scales where particles should no longer be directly interacting with each other. And yet, the plasma behaves as if the particles are still collisional, so effectively collisional. And this enhanced collisionality must come from some sort of complicated particle magnetic field interaction that we do not fully understand yet. And I think maybe you're getting at the slopes we're measuring, right? So as you can see, so these three solid lines are the three clusters we looked at first. They have different slopes, but they're all steeper than the Kolmogorov relation, which is weird. We still don't know why. There are many proposed explanations. My favorite, and it's still my favorite, is simply that we're actually not looking at the cascade. I think the signal is dominated by the behavior of the driver itself, which is the black hole feedback, and it's just a terrible driver of turbulence. We're not seeing a cascade, we're seeing the behavior of the driver. But it's sort of a less interesting explanation. There are maybe my second favorite explanation is maybe we're seeing some sort of partial dissipation of some compressive modes in the system, and maybe you have to dissipate because we are probing very close to the mean free path. Theoretically speaking, you would expect some partial dissipation, and there are other, I think, more wacky ideas out there. Ciao.
Yeah, so L to the 1/2 is what people see in molecular clouds and the
Supersonic.
Larson's laws that you mentioned earlier. And that
This
seems
is
to be
not
directly connected to shocks there.
But yeah, so
So
that partially is related to the partial dissipation, right? So if you have shocks, then you dissipate more energy on larger scales, which would make your slope steeper. But as you can see, a lot of these are even steeper than half. And because of the projection effect, we expect the real slopes to be even steeper. So not, it can't be explained away with supersonic turbulence. Yeah. And because I've turned into an observer, the answer to every question is we need more data, right? So then we look at more galaxy clusters, look at more structure functions, and they'll, for the most part, look like what we've seen already. But one thing I really want to comment on is because of the steep slope that we're measuring, we actually infer a very different turbulent dissipation rate or turbulent heating rate, right? So what these slopes mean, steep slopes mean is the amount of kinetic energy, turbulent kinetic energy on these small scales is actually much lower than what you would expect if you were to extrapolate from these large scales, assuming a Kolmogorov cascade, right?
So I saw you just flashed, like CO 1 to 0 observations
Oh.
on this supercluster.
Yes,
So,
some of these have CO, yeah.
this is not my strong suit at all, but how do you disentangle turbulent motion due to the black hole or this kind of large scale turbulence with the innate turbulence that you just get in those clumps from gas?
Great question. I'm not really, I don't think I'm probing the internal turbulence of these clouds. I treat these clouds as tracer particles. But sure, you will have pairs of pixels within clouds, but we also do not see any slope change in the structure function. So to me, that suggests that there's not much of a difference between turbulence between clouds and within clouds, right? Because like, let's say if turbulence is a lot weaker within these clouds, then you would expect a steepening in the structure function, right? But we don't see that. So I think everything is moving together, kind of like in the ISM, right? Regardless of the phase.
Well, just to follow up on David's point, if they are star forming, then gravity is playing a role.
Oh, yeah,
right?
yeah, so, no, like.
That could affect
I
the.
want to look at small, yeah, so I'll mention a smaller scale observation in a bit. But one first, claim victory.
These are
because-
larger scales, so.
Yeah, so this is, I'm still talking about the larger scale stuff, right? So the previous claims of turbulence being important were made based on X-ray observations, and they're probing these really large scales, the driving scales. And there was nothing wrong with their claims because that's all they can get with the 5 X-ray photons. And so they would have to assume a Kolmogorov cascade and get a decent amount of turbulent heating, right? But if you actually see the effective power spectrum, then you would see, oh, there's much less turbulent kinetic energy on small scales. And so we can measure the inferred turbulent heating rate if we only had information about the large scale motions and compare what we get with our small scale measurements. And so each vertical line represents a system. The top dot is what the X-ray observers would get most likely. And so you would infer a pretty high level of turbulent dissipation rate and more or less balance and radiated cooling. But if you were to use what we can get from these optical observations, the amount of turbulent dissipation would be smaller than 10% of what you need. And that's in perfect agreement with numerical simulations, including mine. So when the observations agree with simulations, the observations must be right.
Since the AGM power correlates roughly with the radiative cooling rate in these costumes, I guess this would imply that the turbulent heating rate also correlates with the AGM energy injection rate. But I wonder if it's tighter or just as wide.
Good question. We didn't look at it.
Because ultimately, where is this turbulence coming from? Is it coming from purely thermal instability, or is it coming from jet-driven turbulence, or what?
Nobody asked me that question. Everybody was mad that the amount of turbulence is so small. Nobody said, wow, why do you even have turbulence? I mean, stuff is moving, so. And so if you're asking me about the
Well,
effect of
I'm curious
viscosity,
about the Coupling of the jet to the
Oh.
ICU,
oh yeah,
right? And so the problem is that the jet really kind of injects energy in a very particular direction.
yeah,
But you really, in order to stop the cooling catastrophe, you know.
yeah, well,
really
okay,
need
so
something
far,
to
so
isotropic.
far, I don't think I've shown turbulence yet. Because I don't think I've seen the cascade.
Right,
Uh-huh. So in a way, so far, if you ask me what I believe is the right interpretation of the observations, I would say I haven't seen cascade, but here's the cascade that I think we saw in one case. Where we have the longest filamentary structure, about whatever. So when we look at the structure function of the really, really long filaments, you see a clear break on small scales. It goes from some steep slope to, I think, a Kolmogorov like slope. And I think this is finally, we're seeing a transition between what's dominated by the driver's behavior and the expected cascade of turbulence. And in this case, it could just be driven by structural formation, it could just be the underlying cascade from structural formation, but on these larger scales, it's dominated, the signal is dominated by the black hole feedback. That's my interpretation. And I think we also see a hint of as the same story in M87. So this is the M87 system. Usually you see the beautiful radio data. Now here we use contours to show you the radio, and the red is the filaments, the cool stuff. And if you zoom into this little blob, there's ALMA detection of molecular gas, and the structure function of the molecular gas shows also this clear break that goes from steep to something that kind of looks like a Kolmogorov. So I think there is cascade, but it's just at a very low level, and you can only see it if you go to very small scales and or you go far away from the black hole.
Another silly question. So before I'd asked about whether it's an outflow or inflow, and you said there's evidence of both. You've also said that there's simulations. And so when you talk about those shocks and sort of in the middle of this picture, which direction are they?
The shocks are going out.
Okay, so there's the low speed gases on the inner, or towards the center of the cluster or towards the outside of the cluster? Like which side is hotter?
Well, behind the shock could be hotter.
But behind is towards the center,
Yeah.
right? So that then it's an inflow, right?
No, oh, well, okay, so these filaments are not volume fitting. And maybe it's not, but it should be clear from this, right? So you would see a pixel as long as there's anything along the line of sight. But these things are very sparsely distributed. So these, I think of these filaments as really just like leaves flowing in the air, kind of like that. So
So like a local.
they're, well, the filaments, I treat them as tracer part in this study. They're very non-volume, and the shocks are going through your volume fitting hot plasma. Yeah. And if you're thinking about shocks affecting the individual filaments, we can talk about that. If there's some observations of like shock blob interaction in some of the systems, but for the most part, these filaments are just there. Okay, so I mentioned that to see Kolmogorov, we can, one way to do it, one way to see it is we move away from black holes. And you can move much further away from the black holes all the way to cluster outskirts. And in cluster outskirts, there's also multi-phase gas that can be found behind the so-called jellyfish galaxies. Some of you actually have mentioned jellyfish galaxies to me when we were chatting. So these galaxies are moving at really fast speeds through the intra-cluster medium. And they're moving fast just because they're falling into a very deep gravitational potential, right? They're moving at something like 1,000 kilometers per second. From these galaxies' perspective, the hot intra-cluster medium acts like a hot wind blowing onto the galaxies. And the ramp pressure pushes the gas to form a tail behind the galaxy. And that makes the galaxy look like a jellyfish, and that's why they're called jellyfish galaxies. Here's a lab experiment demonstrating that process. And so these tails, like I said, are also multi-phase, meaning there's the hot component that you see in the X-ray. There's the cool or warm, depending on who you ask, component of 10 to the 4th Kelvin gas that shines in H alpha. Also CO molecular gas that's forming stars. And so we looked at one of the really well observed jellyfish galaxies, ESO something, blah, blah, blah. Anyway, so this is the velocity field of that big tail. As you can see, this time there is a large scale outer motion, right? There's more red on one side, more blue on the other side. Well, that's because the galaxy that's being stripped is a disk galaxy like our Milky Way is rotating. And so the rotation remains in the stripped tail. And my collaborator, Roncino, modeled this rotation, and he looked at the rotation with a moving window to look at how it changes as you move further down the tail. And what we found is rotation gradually declines, and at some point the tail becomes consistent with not rotating anymore. And so once we have a rotation model, we can remove this rotation and just look at the residual velocity. And now that looks random and possibly turbulent, right? And there are many reasons to think that this tail should be turbulent. This is gas stripped from the interstellar medium of a Milky Way-like galaxy. And we know our ISM is turbulent, so there should be some frozen in ISM turbulence there, right? The cool clouds are also rubbing against the hot ICM. And so there should be Kelvin-Helmholtz instability developing. And so my new student is doing cool simulations of this process. And as these cool clouds become co-moving with the hot ICM, they may also pick up large-scale ICM turbulence if there's. So a couple of years ago, I analyzed the tail of this famous jellyfish galaxy that I don't remember the name of. And also using a moving window, I computed the velocity structure function of the gas. And what I see is, well, first it starts with something that's exactly sitting on top of Larson's relation for our own Milky Way turbulence. The first frame is basically just looking at the galaxy itself. And then turbulence quickly grows, right? And then it saturates at some point. With my back on the envelope calculations, the growth time and amplitude are both consistent with the growth and saturation of Kelvin-Helmholtz instability. So I think we're seeing the growth and saturation of Kelvin-Helmholtz instability in this system. There might be a hint of the tail perhaps picking up some large-scale ICM turbulence. It's really just a hint.
A question about this plot here. If you scale the x-axis by some mean paths at different locations, can you unify all those curves to be a single curve?
Mean free path?
Well, all those different colored lines look like they're just shifting.
Distance.
Yeah.
You mean up and down?
Or left and right. So I'm just thinking, is there like a universal curve that describes this power?
Well, I claim it's okay with very limited dynamical range. It's consistent with Kolmogorov. This that part. It's very limited. So this is affected by seeing.
Okay.
I learned that a few years ago. So it's the atmosphere. Turbulence. Yes. So you don't trust anything here. And on larger scales, I think there's complicated driving different scales. So really I think just this little part is the cascade, and it looks consistent with Kolmogorov, let's say.
So actually on that front, so the fact that there is atmospheric turbulence and you're restricting the data in that gray area and not considering it, but it still looks smooth and continuous, makes me worry about the rest of it as well. Right? So there are now digital twins.
It's consistent.
So there are digital twins for galaxies, there are digital twins for clusters now, and you can imagine putting in some kind of velocity profile into the outflows from these things, and actually running your pipeline to get the velocity structure function on simulated data and seeing if you recovered what you put in. What are the uncertainties? What are the systematic uncertainties in getting the velocity structure function itself?
I have not done the full mock observation, which would be really, really difficult, right? Modeling the entire rigid transfer and everything. Other people have looked at sort of cheap mocks, right?
Yeah.
You can make some just cheap, not mock, but like cheap mock, and then do some Gaussian smoothing to mimic. There's just some steepening of the structure function from smoothing. And we did the experiment too. We just applied another smoothing to the existing data to see how it further affects the structure function. So it would kind of complicated. So it kind of depends on the slope. If it's Kolmogorov, then you would see a noticeable steepening near the seeing limit, the smoothing size. If it's steep, you actually don't see much of a slope change here, and it's more of a global shift downwards a little bit. So I'd say it makes a little bit of a difference, but doesn't affect any of the conclusions. That makes you feel better. But I am interested in looking at maybe JWST data because there's atmosphere there, and I haven't done it, but I think there's data to see what the sort of intrinsic slopes are without seeing. Yeah, but don't worry, we've done tests. It's fine. But to me, the most exciting part is actually we're probing turbulence below the electron mean free path, the Coulomb mean free path here. So as I mentioned earlier, Coulomb mean free path for the hot plasma in cluster outskirts would be on the order of 10 kiloparsec, so the size of the galaxy. And so all of this is turbulence below the mean free path. And again, it's like I said, it's where the particles should no longer be collisional, and yet the plasma seems to behave collisional. And so this is just if we were to just use the simplistic calculation and say how much suppression you have to have on the Spitzer viscosity, then we'd say it's suppressing Spitzer viscosity to 0.01% or below with our new observational constraints. And the most popular theory for the effective viscosity in the ICM actually says that the effective viscosity should be on the order of 5% of Spitzer. And that's you might have heard of the Brzezinski viscosity, right? So in a way, we actually rolled out Brzezinski viscosity. And that possibly implies that magneto-immutability, self-organization is important. If you ask me to explain that, I don't even think I can do a good job. But it's just like some more complicated plasma stuff is probably doing things. But, you know, I think it's a very exciting time that we're actually probing microscopic plasma scales in a big galaxy cluster. And so this is a paper from last year where the observers looked at more systems using the same method and just confirming what was already found with that one system. You see turbulence in all of these jellyfish tubes. Okay, so to summarize, I hope I've convinced you that cool clouds can be used as really cool tracers of turbulence in the hot plasma that is hard to observe directly. Of course, a lot of this relies on the assumption that cool clouds are faithful kinematic tracers of the hot plasma. And we don't know for sure that that is true. I think we need both numerical simulations and observational work to try to help us figure out how good the coupling is. And we detected non-Kolmogorov turbulence. I don't even know what to call that. Call it non-Kolmogorov turbulence for now in cluster centers. We still don't really know how to interpret it. But I think one thing I believe for sure is that turbulent dissipation is not the main mechanism for black hole feedback to operate. And then in cluster outskirts, we can now probe scales below the Coulomb mean free path, and we put really unprecedented constraints on the effective plasma viscosity there. But we still don't have a full description of the effective viscosity in the SEM plasma. I think there's a lot of exciting work waiting to be done there. Thank you.
There's been a bunch of questions during the talk already, but we have time to squeeze in just maybe a couple more. Let's start with you and
It's a big method.
Thank you.
So, you mentioned that the optical observations suggest that the turbulent dissipation is kind of a minor effect consistent of simulations. But that also implies that the X-ray folks, their observation or their implications are somewhat at odds with this model. So why did we derive the turbulent dissipation that would be higher than the optical observations?
It's because the agreement is right here, right? But the X-ray observers would infer a turbulent dissipation rate using a Kolmogorov
Extrapolation.
extrapolation, right?
I
So
see.
then you would get even if just extrapolating from here, you can see there's a difference between what you would extrapolate and what we are measuring.
Understood. So
Yeah.
it's not that the X-ray observations were wrong, it's just
No.
that the
It's
their
limited.
extrapolation were incorrect.
Well, they're limited by the data they have. Yeah. No, they're not wrong. They're good observers.
we could have named them Charles.
Thanks for the fun talk. I'm gonna get a little crazy now.
Now?
So one tracer of the ICM that I noticed is absent here is the SC effect. I'm wondering, assuming you have the signal, is there anything you could do with the SC effect in these supermassive clusters? Can you trace similar scales?
No. Well, you said assuming you could, then yes, but we don't. Right, SC has even poorer resolution. Oh, but you should learn more about TOTEC. So UMass has a telescope called LMT, and we're putting a new instrument on the telescope. It's called TOTEC. You might be able to explain it better because I'm only a fake observer. I know there's a thing that you can add to the telescope. So then.
It's called a camera.
Oh. Thank you. Okay, so.
Yeah, it's at 150, 220, and 270 gigahertz.
There,
That covers
yes.
the signal.
So it's supposedly
50 meters. So
that, it
5
can
times
measure SC with the best resolution.
Mhm.
And
Spatial
so,
resolution.
yeah, the best, you just did the calculation and it is best resolution, right? So not bragging. Okay, yeah, so. But it's still, I mean, it's far from these scales. I do think it might still be interesting to probe the large scale turbulence. Yeah, but right now, it's not helpful for small scales.
Charles?
May I?
Sure. So I'm really confused about this velocity.
Hello?
So is it 1/3 for Kolmogorov?
Yes,
Okay, so
because it's
then,
the
then
structure, yeah.
sorry.
Yeah. Anyways.
I don't
uh-huh,
know if you, I don't know if you can hear me. I lost you.
That's right, that's right.
Okay,
Mhm.
but it's a projected statistic. So does that, I'm confused about how that might change things.
Yeah, so you asked that earlier,
Okay,
if all these clouds were sitting on a sheet. Then this would just be the true structure function. But they don't assume that they happen to sit on a sheet, so they're three-dimensional, okay? So as I mentioned earlier, this projected structure function should be somewhat shallower than the true 3D structure function if we were ever able to obtain that. I don't think we can ever do that, right? So
so
there's some artificially boosted power, I believe, on small scales. But it's not gonna change any of the conclusions. It's only gonna make it even worse, right? So it's gonna make it. So in theory, the true slopes should be steeper, I believe.
And just to check, is there any questions online?
May I?
Marcos is speaking, but we're not, maybe is your laptop,
Good, yeah.
Are there any questions online?
Yes.
he was speaking, he's still speaking,
But nobody was hearing you. That's what it is.
Can,
Yeah, so,
Have that up?
can you hear me?
you do it.
well, we're getting near time, so maybe, if Telemarcus is having audio issues, we can get an email to the speaker, then, you guys can touch base after. Let's thank our speaker again. Lots of great questions, and I'm sure there were more. If you'd like to have dinner with our speaker, we'll meet in the lobby at 5:30.
And you can email me later.
Hopefully. I think,